Welcome back to the next video, everybody. Today's video will be on the local Langlands conjectures and what we'll need from them to discuss Langlands tunnel. We'll be looking first at the local Langlands conjecture in the Archimedean case. In the case, our field is R, and we'll call the local Langlands conjectures just LLC from here on out. Okay, what is the Weil group of R? So what is W sub R? The Weil group W sub R is an extension of C star by Z mod 2Z. So that means we're looking for something that fits into an exact sequence like this. Okay. And what extension is it? It's the Weil group. It's C star union J C star. What is this J? Well, we'll just say J squared is a variable whose square is -1. And we'll also give it the property that JZ, J inverse Z bar for Z and C star. There is a natural surjection as expected phi from W sub R to the Galois group of C over R. What does it do? It sends C star to 1 and it sends J C star to C, where C is complex conjugation. Okay. What we want to do is study the set of equivalence classes phi of GLN over R of n-dimensional semi-simple complex representations rho of W sub R. What is a semi-simple representation? It's just a representation that's a direct sum of irreducible representations. Let's look at some examples. It turns out the one-dimensional reps of WR are of the form, those things that are equivalent, let's say mu, are equivalent to representations tau epsilon. What do I mean by this? So representations that take Z and C star to absolute Z to the T, where the absolute Z means the absolute value on C, and here T is in C, and where J maps to epsilon and epsilon is plus or minus 1. So these are all the one-dimensional representations of the characters of W sub R. So you can see CSS page 176 for details about this. So again, we're looking at all representations that are equivalent to one of these representations. How about the two-dimensional irreducible representations of WR? Those are just all induced from some character of the form Z maps to absolute value of Z to the T times Z over absolute value of Z to the M power of C star, where here T is in C and M is just some natural number. And as a matter of fact, this sort of takes care of all the semi-simple representations of W sub R, because every n-dimensional semi-simple representation of W sub R is a direct sum of some number of these 1- and 2-dimensional irreducible representations that we just discussed. So it's pretty easy in this setup. Okay, what is the local Langlands conjecture for GLN of R? So local Langlands conjecture, but it's a theorem. There's a well-defined bijection, rho with pi of rho, between phi of GLN over R. So that is the set, I define that up here. That's the set of n-dimensional semi-simple complex representations, rho of the Weil group, W sub R, and pi of GLN over R, which is the set of classes of irreducible admissible representations, pi of GLN of R. And moreover, the so-called L and epsilon factors assigned to rho and pi are preserved by this correspondence. Okay, that bears some explanation. So for the proof, you can see Langlands on the classification of irreducible representations of real algebraic groups. In fact, this gives a proof in the more general case that we're representing a reductive Lie group. Okay, the definitions and the proof of the preservation of the L and epsilon factors is contained in Jacquet principal L functions of the linear group. This is in Borel-Castleman part 2. And then I would just highly recommend that you watch Buzzard's MSRI Summer School lecture playlist, Automorphic Forms in the Langlands program on YouTube, for a more general framework and understanding within which all of this sits. Okay, how about the case F equals C, right? I mean, you might wonder if we're going to ever need to consider that field. We don't, but I'll say something about it. The Weil group of C is just C star. And every n-dimensional semi-simple representation rho of this Weil group is a sum of characters mu sub I. And these characters take the form Z over Z bar to the M sub I times absolute value of Z to the T sub I. And the M sub I's are just integers here. Okay, there are no discrete series. I defined a discrete series a few videos ago. And if I give you such a rho, the pi of rho that we get from rho is the unique irreducible quotient of the representation induced by the character mu sub 1, mu sub 2 through mu sub n. And how do you arrange the mu's here? You arrange them so that the real part of T1 is bigger than or equal to blah, 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 the real part of T2 and so on all the way down until you get to the real part of T sub n. Okay, and these T sub i's here are just complex numbers. They're like the T and C's from up here. Okay. So we're doing the local Langlands conjectures, right? So we just discussed all the Archimedean theory. What about the non-Archimedean theory? What about the p-adic situation? So now let's let F be a p-adic field. The Weil group of F, W sub F, is a dense subgroup of G sub F equipped with an isomorphism from the abelianization of itself to F star. And I mean, I'm not telling you, I guess, that W sub F exists, but like implicit in this discussion is that it always does. I would see Tate number theoretic background for discussion on that. What is this abelianization? It's just think of the closure of the abelian part of W sub f if you've never seen abelianization before. You're basically modding out by the closure of the commutator subgroup. Okay, so, well, what are the one-dimensional complex representations of the Weil group here? There again, just the irreducible admissible representations of characters, if you like, of F star, which is thought of as GL1 of F. Okay, just as in the Archimedean case, it's the same thing. But unlike in the Archimedean case, there are now irreducible representations of the Weil group of arbitrary dimensions. This does complicated things, but it turns out for us, we don't need the general theory. We only need the following. I'll give you p-adic LLC for n equals 2. That is a theorem. To each two-dimensional semi-simple representation rho of the Weil group, we may associate a unique irreducible admissible representation pi equals pi of rho of GL2 of F with the following properties. Essentially, omega sub pi of alpha, which we'll define to be pi of the scalar matrix alpha, is the determinant of rho of alpha times I. And for all characters chi of F star and all characters psi sub F of F, the following hold. L of S pi tensor chi equals L of S rho tensor chi. L of S pi tilde tensor chi inverse equals L of S rho tilde tensor chi inverse. And epsilon of S pi tensor chi comma psi sub F is epsilon S rho tensor chi comma psi sub F, and all irreducible pi arise in this way. Okay, now I owe you some notation here. What are the L's and the epsilons and the tildes in particular? These are the L and the epsilon factors I talked about earlier. They are defined in Jacques Langlands on the left-hand side anyway. What about the L and epsilon factors on the right-hand side? They're defined in Langlands on the functional equations of R and L functions. And what is tilde up here? Like, what are all these tildes? That's just the contragradient representation. That's the representation on the dual. Okay. On the general proof, I have some remarks. Existence and exhaustion are fairly easy to prove, except for the case that rho is irreducible. You can see Kutzko, the local Langlands conjecture for GL2 of a finite field for the case where F is any field, for example. How about uniqueness? That's covered in Jacques Langlands in chapter 2. Okay, let's look at some final examples here. Let's let K denote the residue field of F, lowercase k. The Weil group W sub F then consists, it turns out, of those elements of the Galois group G sub F, whose image in the Galois group of K is an integer power of the Frobenius generator of G sub K. That's nice. That's a great way to think about W sub F. Okay, well, that just means the inertia subgroup I and G sub F is actually just in the Weil group. And so we can talk about unramification then, right? So a representation rho on the Weil group to GL2 of C should be unramified if it's trivial on I, of course. Okay, well, by construction, WF mod I is just isomorphic to Z. And so rho is completely determined then by where it takes the class of a Frobenian element in W sub F. That's great. Okay, well, let's suppose that after conjugation, if we need, rho of Frobenius is this nice kind of scalar looking matrix, p to the negative S1, 0, 0, p to the negative S2 in GL2 of C. What will the corresponding pi of rho be for this type of rho? Well, the corresponding pi of rho of GL2F will be the unramified induced representation, none other than pi of mu1, mu2, where mu sub I of x is absolute x to the SI. In other words, the local Langlands class T sub pi of rho is just the matrix mu sub 1 of p, 0, 0, mu sub 2 of p. And that's conjugate to rho of Frob. All right, so that is the local Langlands situation. Starting next, remember, we're really trying to look at the global situation because we kind of have a global problem on our hands. So starting next video, which might be tomorrow, might be Monday, we'll start looking at the LRC, the Langlands reciprocity conjecture. So we'll start looking at the global Langlands picture. So I'll see you then. Thanks for watching.